Hi, welcome. In this video, we're just going to go over some common problems in concurrency. So in the operating systems, we're just going to talk about some common issues dealing with process synchronization. So let's start talking about some software solutions, and then we're going to talk about some classic problems, included the producer consumer, or in other words, I got to get my pen here. The producer consumer is a bounded buffer problem. That means it's a buffer with a particular size, a bound on it. The dining philosophers, how processes can share multiple instances of a resource, readers and writers, and then we're going to talk an overview of deadlocks. So concurrency issues include what can happen. You can have deadlocks, race conditions. Race conditions happen when the order in which critical data is accessed. If it's not accessed in the right order, then you don't get the correct output. That's a race condition. You also could have starvation. That means where some processes are accessing the critical data and other ones are getting locked out and not getting any chance to get in there and access that data, or getting starved. Just like in CPU scheduling, they get starved for the CPU. Here you could have issues in which they get starved for the shared data. So some strategies, we have locks and semaphores and condition variables and monitors. A little bit about these different things. Locks have busy waiting. The idea of a condition variable is to block while waiting. A semaphore is a global variable with three. We already went over this in the last module, but it has initialization, wait, and signal. The thing about usually a semaphore, the wait is going to decrement and the signal is going to increment unless the semaphore works at waking up processes that are in line or waiting. And then you have monitors. This is encapsulating the critical section and only allowing one process to be active in a monitor at a given time. So you want to avoid nested locks and you want to avoid circular waits, meaning P1 waits for P2, P2 waits for P3, and P3 waits for P1. Obviously, that's going to cause issues. You want to use timeouts or mechanisms to reduce starvation. Like I said before, starvation means that you're not even getting access. And you want to use atomic operations to avoid race conditions. Atomic operations means that the entire operation occurs or it goes back and starts all over from the beginning. So you can have a set of instructions, but they all need to be created as if they are one operation, and the whole operation has to happen in order for it to be done, to be an atomic operation. And if it does get stuck somewhere in the middle, it has to go all the way back to the beginning and be like it never happened. That's what atomic means. And you can validate programs with tools. All right, so a monitor, the idea of a monitor is that you encapsulate the data and you only allow one process to be active. So if P1 and P2 and P3 all want to access the critical data, you would have some kind of request procedure. Well, even while P1 is doing the request procedure, no other process can do anything, any of the procedures or any of the instructions that are inside of the monitor. While P1 is inside of this monitor, P1 is the only one active in the monitor. The only way that P2 can become active in the monitor is if P1 finishes doing the instructions or P1 waits on some type of a condition, because you can add condition variables to monitors. So that's the idea of a monitor. And only one process can be active at a given time. But if you wait on a condition variable, then you're no longer active. So you do have condition variables in monitors. So if you go to request and it's not available, then you could be put onto a condition to wait. The difference between a wait in a monitor and a wait in a semaphore is that the wait in a monitor has no effect on any variable. And if you remember, the wait in a semaphore, many times the wait will decrement. And so it will change the outcome if if a process waits and decrements the value of the semaphore. So let's talk about some classic problems now. The bounded buffer or producer-consumer problem, the readers and writers, and the dining philosophers. So the first one we want to talk about is the producer-consumer or bounded buffer. Bounded buffer means that the buffer has a size, and you have a producer, you have processes that that produce data and put it in the buffer, and you have consumers that consume data from the buffer. That's the idea. The producer creates, the consumer takes data out. So you want to coordinate and make sure that you don't have race conditions. You want to make sure that the buffer is, you don't want to have any process try to add anything to the buffer if it's full. You don't want to have a process trying to remove something from the buffer if it's empty. You want to have only one process accessing the buffer at a time so that you are making sure that everything is coordinated. So the producer must wait if the buffer's full, like I just said, and the consumer must wait if the buffer is empty. So how do we solve the problem? You can use a mutex lock for mutual exclusion or semaphore, and you need condition variables for the coordination. So you can also use a semaphore for the mutex, or you can just use semaphores for the whole thing. So you have one, you would signal when it's not full so the producer can add, and you can signal when it's not empty so a consumer can remove. And this mutex right here, like I said before, this could be a lock or a condition variable depending on what you're doing, or it could be a binary semaphore, or you could use a binary semaphore for that. So you want to make sure that things go in order and that it's efficient. So here's the concept. You have your consumer, if it's full, oh, I have to initialize here. So you have n buffers, and you would use, like I said, this is the mutex. So this is a binary semaphore, which is initialized to 1. A binary semaphore, this is the mutex right here. So the mutex is where you're going to wait here to remove and wait here to add. So this mutex right here would be initialized to 1 because if you don't remember, initialization to 0 would mean it's not ready, but initializing to 1 would mean it's ready because no one's there, and then whoever runs the first wait is going to change the value to 0. So you also have a semaphore that would be initialized to 0 because there is nothing, because it's not full yet. And then the empty would be initialized to n to count how many empty slots there are. So this is the idea. This one, the consumer is going to have to wait if it's full. The producer is going to have to wait if it's empty. Then the consumer would remove an item once it's not full, once it is full. So the consumer here is going to have to wait actually on full if it's empty, right? So you can't consume anything if there's nothing in there. So it's going to have to wait on that. And then if there is an item in the buffer, then it's going to go in there. It'll have this mutex where it will be the only one active. Then when it's done, it's going to signal that one has been removed. So here, this is the opposite. This is going to have to wait. If it's empty, it's going to produce. And then here's the mutex that it's going to go in there and be in the buffer by itself. And then when it's done, it's going to signal that it has produced something and added something. So here the consumer wants to make sure that there's something to consume, and the producer wants to make sure that it's not full. Right, so here is how here's an exercise where you can track it. So our buffer size is 4. That means we have 4 buffers. So we're going to, our mutex will be initialized to 1. So whoever gets there first is going to hold that, is going to be able to get in there. We're going to initialize empty to 4, and we're going to initialize full to 0. Let's do 2 produce calls and 1 consume call. So if you're going to trace along here, I have all of this here to remind you. We start out with our first, what were we going to do? 2 produce and 1 consume. So our first produce right here is going to wait on empty. Remember that it is going to decrement to 3. So when it takes empty has been initially set to 4. So produce is going to check. It's not, there's spaces. So if it was 0, it would be full. It wouldn't be able to put 1 in there. Then it's going to take over this mutex and change it to 1. Add an item to the buffer. The mutex, change it to 0. So that any other process that's trying to get in there is not going to be able to get in there with that mutex. And then it's going to signal the mutex when it's done and change it back to 1. And then it's going to add 1 to full to indicate that there is something now ready to be consumed. The next one's going to come. Empty is going to go from 3 to 2. Mutex is the same. Take over that mutex. It's been signaled. So here, this one was already signaled, so this wait is okay. And now full is going to be 2. So now the consumer is going to come along, and the consumer is going to check. The value of full is 2. So it's going to decrement full down to 1. Then this mutex has been signaled here. So it'll remove one of the items from the buffer, signal the mutex, and then change empty signals. Remember that signals add and waits decrement. So it's going to signal and add 1 back to 3. So when it's done, the mutex will be back at 1, ready to go. Empty will be at 3, and full will be at 1. So you'll have an exercise similar to this in your homework. So now let's talk about the reader-writer problem. There's first readers and first writers. First readers means that readers have priority. First writers, oh, I don't know what, this is missing something here, but it's okay. So this first writers have priority. The big deal is readers can read as much as they want, but when a writer comes along, the writer's going to change it, right? So you either have to let readers read until they're done reading and then the writer changes it, or you have to make the writer block everybody else out so the writer can write. So then the readers are going to get the latest updated information. So it's a very, this is a very big deal because, you know, when something is, sometimes you need to have something after it's been written. So there's a lot of different ways to do this. We're just going to talk about reader priority, which is a little less complicated. So what a reader's priority is also called first readers. So first readers means that readers have priority, and first writers means that writers have priority. So first readers, the first reader will lock out all writers when it enters. So readers don't have to lock out readers, they only have to lock out writers. As long as there are readers, then the writer will be blocked, and when the last reader exits, then writers are allowed to get in. A first writer, it's going to block out everyone. So if a writer is waiting, then it has to block everyone. Once a writer gets in, only the writer can be in there. So it has to block out readers and writers while it's writing. So you're going to use first readers when reads are more frequent. And then obviously writer starvation can happen. You would use first writers when writes must not be delayed. So if writing is really important, again, this is an exercise where we're just studying and thinking about these concepts. So a fair solution might be to just balance things in some kind of queue. So here is a table about different, how these two first readers and first writers work. Readers, first readers, we already talked about that. First writers. So with first readers, the readers block out any writers. With first writers, the readers block out everyone. which is fair. They could both lead to starvation. And so let's take a look at an example. So we're going to take a look at a first readers example. In this case, a first readers have priority. So what happens here, we're going to have a mutex that's going to protect the read count. So the read count is seeing how many are reading. So why do we need a read count? Because you need to make sure that read count is 0 before a writer can come in. So you can let 10 readers read, but each time you're going to have to update the read count so that as soon as the read count gets to 0, then the writers are allowed to get in there. And then you have to have, so you have a mutex which goes around the read count, and then you have this variable right here, WRT, which controls access to the shared resource. So they're both initialized to 1 because no one is trying to access anything, but remember that weights are going to decrement. So what is a reader going to do? So the reader is going to go in there, and it has this mutex first. This is the read count mutex, right? So what it's going to do is it's going to go in there and it's going to block it and not let any other process update the read count. So then it's going to add 1 to the recount. This condition right here is just saying, oh, I'm the only one there. I'm the only one there. So I'm the one that's going to block the writers. Okay, then I go out there. Now I'm going to read. And now I'm going to decrement. And now I'm going to say, oh, now I'm the last one out there, so I can signal and let a writer in if a writer is waiting. Okay, so that's this part right here. If the read count is this is the first, so the reason that we need to check if I'm the first one is because if I'm not the first one, this WRT is going to be changed to 0. So let's look at that again. This is the mutex right here for the read count. So I'm going to take this mutex, I'm going to change it to 0 so that anyone else trying to get in there can't get in, because remember, wait says that if it's 0, you can't get in. Then I'm going to change the read count, so I'm going to change the read count to 1. Now, because I'm the first one, I need to run the wait on this, and I need to change this one also to 0. Block out any writers that try to get in. So then I signal this back up to 1 because other readers can get in. I'm going to read, and then I'm going to let other readers get in. And now I'm going to change read count back down by 1. But if after I signaled this mutex and allowed other readers come in, so say now the read count gets up to 3, so 3 have read. They've used this mutex right here, and 3 have read. Then the first one to go in here to put the read count down, it's going to change it to 2. It's going to change it to 1. So the last reader that finally checks the read count is 0 is the one that's going to signal and let the writers in. So take a little time to look at this. It's not that complicated. It just have to think about it. So there's 2 different reasons why you're going to wait on the mutex. You're going to wait on the mutex so that you can change what the value of recount is. And then you're going to wait on the mutex again to change the value of this read count. And then this semaphore right here is to keep the writers out. So if you're the first one in there, you gotta block out the writers. If you're the second one in there, the writers have already been blocked out. And if you're the last one in there, you can signal and let the writer get in. So the writer is just going to wait, and then it's going to write when it gets a chance, and then it's going to signal when it's done. So this is the first readers. It's not as complicated as the first writers. So we're just going to go over this exercise, but I do have in your notes a little bit on first writers. Okay, so here's a scenario. We have, oh, I didn't put the scenario. So, oh yes, here's the scenario. We want to have one reader, a second reader, then a writer arrives, then the reader finishes, then the reader two finishes. So we have two readers, one writer, and two readers. So we're going to show the scenario and go through what happens. Okay, so what do we want to find out? We want to show what is the value of mutex after, what is the value of WRT after each operation. So when the reader starts, what are those values? When this reader starts, what are those values? When this writer arrives, what are those values? This values and this values. When does the writer get to write? Does the writer get to write right when they arrive, or does the writer have to wait? Does this cause starvation? So here is the scenario. So we have, just to remind you, this is what the reader looks like and the writer looks like. So the first thing, the reader 1 starts, changes the mutex from 1 to 0. That means that it's the only one that can get in there. So it's also going to change this mutex is to 0, and it's also going to change WRT to 0 to block out any writers. Now it's going to signal this because it's going to go in and read now. So the reader 1 is in there reading now. It just needed this mutex to change the read count. Now reader 2 comes in and it's going to change the read count to 2, and it does not need to try to lock WRT because it's already locked. And now the writer arrives, but it cannot get in there, so it has to wait. So when reader 1 finishes, he changes read count to 1. When reader 2 finishes, reader 2 is the last reader. So finally, reader 2 is going to signal WRT. So when it signals WRT, then the writer can proceed. So the writer does not get starved, but the writer does have to wait until both readers have read and finished reading, started reading and finished reading before the writer can get in there. Obviously, that's because this is the first readers. All right. Now we're going to talk about the dining philosophers. The dining philosophers is a scenario where you have 5 philosophers that sit around a table and they want to eat rice. The problem is that they only have 5 chopsticks, and each philosopher needs to use both chopsticks in order to eat. So obviously it's not real life, it's an exercise to understand some of these problems. So the idea is that you could pick right or left to go first, but the idea is that if this philosopher here wants to eat, he's going to pick up this chopstick, go ahead and eat, and when it's done, it's going to put down this chopstick and put down this chopstick. So if while this one is eating, this philosopher decides he wants to eat, he's going to pick up this chopstick and have to wait for that one. So there are different issues about this, because should you allow a philosopher to pick up a chopstick if they're not able to pick them both up, or because then they would be picking up one and waiting for the other one, and that could cause a situation which could cause a deadlock, which we're going to talk about in a minute. So that's it. This is a classic problem, and it's only got 5 chopsticks, and there are things to think about. The thing about the philosophers is that they either think or they eat. So that's why it's called the dining philosophers. They think, they sit there, and they don't eat, and then when they want to eat, they have to pick up 2 chopsticks. Okay, so I already told you all of this. This is 5 philosophers. This is a case of shared data, and one way to do it is to have a semaphore for each chopstick. So like I said, this one is 1, 1, 1, 1, and 1. So when this philosopher he runs his wait, remember that wait decrements. So it's going to change the value of this one to 0. And then he's going to wait on this one, change this value to 0. And then, so what's going to happen is this philosopher is going to say pick up his and change it to 0. But then this philosopher has these 2 chopsticks, and this philosopher is waiting for that one. So there are things you can either say, oh, you pick that up after a certain amount of time. If you're not able to pick up the other one, you got to put that one down. And these are things that we need to consider in as far as synchronization and things that could cause deadlock. So this is what I was just talking about. You would pick up your one chopstick on one side and then pick up the other one. You would eat, then signal. You would put down that chopstick. When you signal, you change it back to one, so then the other one could get it, and then you go back to thinking. So what could happen here? There's problems. I just pointed out. Another problem that could happen is, so here's a problem. These are the philosophers. These are the chopsticks. And this philosopher could pick up that chopstick, and then this philosopher could pick up that one. This one could pick up that one, and that one. And in that case, what happens? Each philosopher has one chopstick and is waiting for the other chopstick. So this is a very classic example of a deadlock situation. The dining philosopher situation is a little, the dining philosopher's monitor situation is a little bit different. It makes sure that you do not pick up. It has this test here. So you only pick up if you're going to pick up both. And keep in mind that if you have 5 philosophers, only one could be active in this monitor at a given time, meaning only one philosopher can actually be doing dining philosophers dot pick up, or dining philosophers test, or dining philosophers put down. So the only way that another philosopher could get in here is if the philosopher goes on to a condition. So if it gets on a wait condition, then while that one's waiting, another philosopher could be active in here in order to do the signal, which would make that one wait. But this solution, if you look at it closely, it does not allow philosophers to pick up chopsticks unless they're able to pick them both up. So now let's talk about deadlocks. So here is an example of how a deadlock could happen in a semaphore situation. So remember that you have wait and signal. So here you have 2 processes. So they're initialized to 1. So P0 has a wait on S. We have 2 semaphores. You have S and you have Q. So this one is so we have S equals 1 and Q equals 1. So what happens here is P0 does this and changes the value of S to 0. Then P1 does this and changes the value of Q to 0. And now what happens? Well, what happens is you've got P0 is stuck here and P1 is stuck here. And the only way for P0 to get past this is for P1 to run that signal. And the only way for P1 to get past this would be for P0 to do that signal. So this is just another, I showed you one example of a deadlock, which was the dining philosophers, and this is another example of a deadlock that could happen. Another concept is starvation and priority inversion. We did talk about priority inversion when we talked about CPU scheduling. So a couple of things that you could do is, in order to avoid starvation, you could have some type of protocol that you have to, with a timer, or that you change a priority to give lower priority a chance to get scheduled, or some kind of way in which you can prevent, lower priorities from sitting there and holding resources or causing starvation issues. All right, so let's talk a little bit now about resources. So in your system, you have a bunch of resources. So the thing is, if you're going to use some resource allocation could be dynamic, and some of it you need to know ahead of time. And I do have other videos that have more of this in much more detail. So this is just going to be overview right here. when a process needs a resource, it would request the resource, use the resource, and release the resource. So request would be, like the entry, and release would be like the exit. And so these are just overview of some of these terms that are going to be coming up. So when you have deadlock, what can happen in a deadlock situation is there are these 4 conditions. And if you have these 4 conditions, there's a very good chance that you do have a deadlock. It doesn't mean you absolutely have a deadlock, because it's possible to have a situation where you have maybe 2 chopsticks, like an extra chopstick or something. But mostly, if you have the situation with these 4 conditions, there's a very good chance that you have a deadlock. And so understanding these, just listing these conditions out, I drew the picture of the dining philosophers because it makes these very clear. So mutual exclusion, that just means, for example, on a chopstick, only one philosopher can have a chopstick at a time. Hold and wait. It's very obvious here that each philosopher is holding one chopstick while waiting for the other one. No preemption. So preemption is a thing that could help to have not have a deadlock, right? So you could get this deadlock, prevent this deadlock from happening by having some type of preemption in there saying, okay, once you pick up your chopstick, you can wait a certain amount of time, and if you don't get your other chopstick in a certain amount of time, then you're going to have to put it down. So that would be preemption. But in this case, with no preemption, we have a very good chance of deadlock. And circular wait. This is very circular. It's very obvious that each philosopher in a cycle is waiting for the other one. Okay, so what are some of the methods that are used for handling deadlocks? The first is to prevent or avoid a deadlock. So to prevent a deadlock, you never let all of those 4 conditions become true. So there are things that can be in place that don't allow all 4 of those to become true. To avoid, you can use some kind of resource allocation graphs, or we have the exercise of the banker's algorithm. You can allow the system to recover. You can allow the system to get into a deadlock state and then recover from it. And many systems, that's why I had that ostrich, choose to just ignore the problem and just leave it up to whoever's using the system or the processes to just restart if something like that happens. Keep in mind that there are some systems that are really hard real-time systems, and that must not allow a deadlock to occur. So again, these are just how to prevent it, not allow it to happen. Mutual exclusion is very hard to deal with because that's the whole point of the critical data. But hold and wait is one thing. Like in the dining philosophers, you can make sure that the philosopher cannot pick up a chopstick unless they can pick up both. In this traffic scenario, you can make sure that a car cannot get into the intersection unless they can pass through the intersection. Preemption, obviously in this traffic, preemption would be a big issue, but in the dining philosophers, I already talked about how you could have one of the philosophers put down the chopstick after they've held it for a little bit amount of time. And you can have some kind of ordering that will not allow the circular wait. The circular wait is a very big deal if that occurs, but there are ways to test to make sure that you're not going to be doing that. All right, so the simplest and most useful model is to have you can declare the maximum number of resources that you need and ahead of time. These are exercises because sometimes it's not obvious how many resources are needed ahead of time, but these are exercises that help you understand these concepts. You can dynamically examine resource allocation and make sure that you don't have a circular wait. That's like a resource allocation graph. And you can use also the banker's algorithm to make sure that if you were to allocate, that it would not give you into a state that is not safe. So here's a deadlock detection wait for graph. So if this is an example to show that how a cycle could occur. P1 is waiting for P2, P2 is waiting for P3, and P3 is waiting for P1. So that is a cycle right there. So this cycle would indicate that there is a very good chance that you have a deadlock. You can also use resource allocation graphs. I have another video that has examples with this. You have request edges, and then you have assignment edges. So if you have a cycle in your resource allocation graph, like P1 wants this resource, but this resource goes to P2, and P2 wants this resource, but this resource goes to P1. Now, one thing is resource 2 has 2 instances, so there's a chance that it might not cause, it might not cause a deadlock because P1 would be able to release resource 2, or P2 would be able to access the other instance of resource 2. So that's the idea, that it does have even if it has a cycle, if you have more than one instance of a resource, there's a chance that it may not be causing a deadlock. The banker's algorithm is an exercise that I'm just going to do this very quickly. I have it in a lot more detail in the next video. So the banker's algorithm is one of those that you need to know ahead of time. So you would know how many instances you have of each resource. So R0 has 8 instances, R1 has 5, R2 has 9, and R3 has 8. So we know how many instances we have of each resource, but what happens is P0 needs to say ahead of time, I'm going to need 3 instances of R0, 2 instances of R1, 1 of R2, and 4 of R3. So then your operating system is going to say, well, I only have 8 of R0, so I'll give you 2 of those, and I'm not going to give you any of R1 right now. So that's the way that allocation works and max. So then there's just what you do is you go through and you do the calculation. So you say, okay, well, P0 has been allocated these resources. This is what they're going to need to complete their task. So you calculate the need matrix by subtracting the allocation from the max. So if P0 has been allocated 2 and needs 3, then this would be 1. 0 and needs 2, this would be 2. 1 and needs 1, this would be 0. 2 and needs 4, this would be 2. P1 has 0 and 0. 1 and 2, this would be 1. 2 and 5, this would be 3. 1 and 3, this would be 2. So do you understand this need is calculated by subtracting the max from the allocation. So your max is 5, you've been allocated 4, you have 1. This is a 1, this is a 0, this is a 2. This is a 0, this is a 2, this is a 2, this is a 0, this is a 2, this is a 0, and a 3. So once you get the need, then what you do is you calculate the available. So how do you calculate the available? Well, R0 has 8 instances, and 4, 5, 6, 7, 8 have been allocated, so there are 0 available at this moment. R1 has 5, and 2, 3 have been allocated, so there are 2 available. R2 has 9, and 3, 4, 5, 6, 7 have been allocated, so there's 2 left, and R3 has 8, and 3, 4, 5, 6, so there's 2 left. So then you go through the processes and you go and decide, well, if I have 0, 2, 2, 2 available, then what are there any processes that would be able to get their work done by using what's available? And then you say, yes, P3 could. P3 has 0, 2, 2, 0. So 0 is less than 0, 2, 2, and 0 is less than 2. So what happens then is what has been allocated to P3 would then be added and come to the available. So now I have 1, 4, 3, and 2. So P3 is done. Now the next one, I use 1, 4, 3, 2. P4 cannot use that because it has 2 of resource 1. The next one I could do could be P2 would be fine. Any of them would be fine. So that's how you do it. And then once you do that, you will see that if I select P0 as the next one, then P0 is going to make available 3, 4, 4, 4. And once that happens, then all of them are available. So then I can pick any order, and one sequence that would be safe would be that sequence. So that is the banker's algorithm. Here's an example of the same banker's algorithm in which it's not going to be lead to a safe state. So let's just do this quickly. So this would be a 1, 1, 0, 2. P1 is a 0, 1, 3, 2, 1, 1, 0, 2, 0, 2, 2, 0. Hopefully I'm doing this right. 2, 0, 0, 3. And 4, 5, 6, 7, 8. So I have 0, and I have 2, 3, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 1. So 0, 2, 2, 1. Let's see. 0, nope. 0, 2, nope. 0, 2, 2, 1, nope. So none of the processes, you cannot, the ones that are available are not going to be adequate for any of the processes. So what you can do to deal with that is you can change your allocation. You can't change the max because that's what they need, and you can't change the number of resources available, but you can change your allocation. All right, so this is an overview. There are more videos that go in more detail on some of these topics, and I hope you enjoyed learning about these concurrency